In this video, you'll learn about AI agents by walking through a real-world practical project. This is not a simple chatbot tutorial. We're building a network of tool calling agents that use real-world APIs to fetch data, generate and run Python code, and write files. We'll cover all important features, so by the end of the tutorial, you feel comfortable writing your own. Step by step, I'll show you how to define the agent, write the prompts, and put the agent work back into the graph. With that said, let's take a quick look at some of the questions and answers generated. We're building a React-style network with LangGraph, starting with the Supervisor node at the top. Our first agent will be a plain LLM that can answer simple queries. The file writer agent will have access to the file system and can read and write CSV and image files. The code execution agent will generate and run Python code in a REPL environment, while the researcher agent will use Tavily search to bring fresh data into the LLM. Vantage will be our real-time market data tool. And finally, the GDP researcher will use APIs from the IMF to bring GDP data. If this sounds exciting, feel free to check out the code from the GitHub repo and experiment on your own. Write your own queries, change the model, change the prompts, and if you get some interesting results, feel free to share with the community. Post them in the comment section or join the Discord server where you can get deeper into the conversation. Let's get started. Before jumping into coding, let's check out the React architecture from LangChain. Let's take a look at the document provided by LangChain explaining different agent architectures. If you follow my earlier tutorials, you may have seen RAG as well as LLM agent networks created with LangGraph that follow the router architectural pattern. But for today's tutorial, I chose React because there are certain benefits. In particular, we're going to use tool calling agents to create this network of specialized agents that will use certain tools made available to them and then synthesize this data into our responses. The React is a general purpose agent architecture integrating three core concepts: tool calling, memory, and the planning aspect. We're going to implement all three of these. And by the way, let's take a quick look at the original paper that defined the React architecture. This came out a number of years ago by the Princeton University Research, Google Research, and the Brain team, which I'd like to be part of at some point. It is called React Synergizing Reasoning and Acting in Language Models. So it's made up of these two words, reasoning and acting, so React. Let's just jump into a quick example so that you can understand the differences between traditional methods and the React. Here the question is, aside from the Apple Remote, what other device can control the program Apple Remote was originally designed to interact with? So this is the React core architecture for agent calling, and this is what we're going to be using today. Let's now jump into our code editor and start our project. In Visual Studio Code, I have a blank project and I've created a data folder where the results will be stored. At the same time, I also have the environment example file, template keys for Tavily, Vantage, and any other tool that we need to use. Currently, it's a blank file because for the first step of the tutorial, we're not going to use any keys other than the LangChain API key, which we're going to need for Langsmith. So with that said, let's create our first graph file and start working on it. I'm going to save this as graph.py. We're going to start by importing OS and then load.env. From typing, we're going to use typedict and literal. And now for the state, we're going to use message state. This again is a new class that we haven't used before, but it's a utility class provided by LangGraph that makes it easier to create message-based states. We're going to use state graph and start and end nodes, as well as the Azure Chat OpenAI model. Finally, we're also going to tap into memory saver because we're going to create a checkpointer memory for our graph. Next, we're going to load .env and define a constant for our tokens for our model. Next up, we're going to define the LLM model. This is going to be the same model that we've used in other tutorials. Feel free to experiment here with your own model. If you have other models that work better for you, perhaps clothes on it, the only requirement here is that it should support agent calling and tool calling, and not all LLMs do that. If you start getting exceptions, if you have issues, just switch to a more powerful model. Now we're going to define the nodes in our agent, and our agent state will be a simple one that will only have one key, which is next. And this will be used by our supervisor agent to determine which node to redirect the flow next. If you remember the chart, we have one supervisor at the top and 6 agents at the bottom. The supervisor will communicate with the state through this variable called next. Next, we're going to define our members. And currently, it's just going to be an empty array because the goal of this step is just to create the supervisor node to start, supervisor, and end. Once we have members added to the array, we're going to compile these options from the members and then add the finish keyword so that the supervisor can get a whole list of all the agents available to the network. Now we're going to define our system prompt for our supervisor agent. And this is super important. To the graph, we're going to improve this prompt and add more conditions. Currently, it's very simple. You're a supervisor tasked with managing a conversation between the following workers. Given the following user request, respond with the worker to act next. Once the system prompt is defined, it's time for us to get the supervisor state defined as well. If you recall, the first state that we defined was for the agent, and now this one is for our supervisor. And now let's define our first node, which in this case is the supervisor node. We're going to take the state as an input to the supervisor node, and then we're going to issue LLM with structured output, passing the supervisor state Pydantic class so that we get this output back, which will be a literal, and it's going to be one of the options array passed. And the options array, if you recall from earlier, is just the members as well as the finish word. So basically this Pydantic class will return one of the worker agents to redirect to next. So this is our supervisor node defined. We'll print supervisor start, we'll print supervisor end, and we're going to issue a simple LLM with structured output supervisor state and invoke with the messages. And then the next will read from the response next key, and then we will just pass it back into the state. Next, let's define our builder, which will take the agent state as a parameter. Let's add our first node to the graph, and we'll do that through builder add node supervisor. Once the node is added, we can add an edge. And this is how we add the edge from start to supervisor. Once inside supervisor, supervisor will decide what node to execute next. Now let's configure our graph memory. And for this, we're going to use memory saver. And this config object is an arbitrary map that will pass to our state graph so that we can identify our threads. But this is a required parameter. Make sure to have this. The thread ID is insignificant. Now we're going to add our members as edges to the graph. So each member will always report to the supervisor. As a reminder, the member array right now is empty, so nothing will report to the supervisor as of yet. Here, the supervisor will populate the next field in the graph state, and we'll do add conditional edges with the lambda, which will then be a function of the next state. So it's a very simple lambda function where we're passing the state as a parameter, and then the return will be the key of the next state. Now it's time to compile the graph, and during compilation, we're going to pass the checkpointer that we defined earlier, this memory parameter. We're also going to get a visualization of our graph. So for that, we're going to use the draw mermaid PNG method, and we're going to store it in the root folder as graph.png. Now it's time for us to create the main loop. Inside the main loop, we're going to invoke our graph, and this time we're going to use the stream method. We'd like the messages from various agents to stream to our terminal instead of one big message being displayed at the end. The important thing here is that we're passing the config parameter. Without this, the graph will not have the memory and it would not remember previous messages. Okay, so this is the main loop, and now we can run our main loop. Okay,
Just a quick summary of what we did. We did the import statements of various classes. We load our environment variables. We set a max token of 2000 for our model, and this parameter can be changed later, obviously. The maximum for Azure Chat OpenAI is 4096. When you first start, it may be a good idea to start low so you can limit the number of tokens that are expended. Then we define the agent state. We defined our members, currently none. An option array would be members plus the finish word. System prompt for our supervisor agent. Then we define the supervisor state by passing a type deck. This is basically a Pydantic class that will return the next as a literal of one of the options. Then we define the supervisor node agent, which will just simply do LLM with structured output invocation, passing the supervisor state as a Pydantic class and getting back a structured output where we just parse the next keyword from the response. Then we added the node, we added an edge, then we added all the members as edges from member to supervisor. So we have a line back from each member to the supervisor. We added a conditional edge, which is a simple lambda method in this case. We compile the graph with check pointer. We're drawing an image, and then we're running a main loop where we're asking the user for input. Unless it's quit, exit, or queue, we continue the loop until the user wants to exit. We can save this now, and we can give it a try. Open the integrated terminal and then type Python graph.py. We have the prompt ready. We also have the graph PNG generated. So let's just take a look at it. It's the simplest of graphs. We have the start node, the supervisor node, no agents under supervisor yet, and the end node. Okay, this is as simple as it gets, but it gives us a good idea of how to build a very, very simple first message. We'll go ahead and type is hi. The supervisor received the message and routed it to the end node. Whatever the message is, we're always going to get routed to the end node because there's nothing else to route to. However, one thing we can do is we can go to our browser now and check out our LangSmith execution graph. So let's just quickly take a look at this. We have the LangGraph. The user said hi. Supervisor responded with the end output. So it's a good idea to have LangSmith wired up into the project right from the beginning. So if we go back to Visual Studio Code now and type another message, let's say hi to, and we're still going to get the same end node. But going back to the browser, and if we check our LangSmith, now we should get another message. And as you can see now, we have hi to, and because we have memory integrated into our graph, both human messages are recorded here in our messages array. I'd like to do a quick experiment here by removing the memory and showing you how that will change the graph execution in LangSmith. Let's just go back to code real quick. First, we're going to comment out this config parameter here. And secondly, we're going to remove this check pointer here. So I'm just going to copy and paste this, but without the config. So in effect, we're just removing now the memory from our graph, and we can still run it without memory. I'll show you how the messages would look. In this new execution, let's go ahead and type first without memory 1. So that's my first message to the graph, and I got redirected to end. Going back to browser, let's check out the browser output now. Without memory 1 input from the user and the end output from our supervisor node. Let's go back to the code editor and type without memory 2. And when we execute the same thing and go back to the browser and check our LangSmith, you'll see that we have without memory 2 as a message, but we did not retain without memory 1. When you don't add memory, communication between agents is not retained, and the messages array only retains the last message produced. Adding memory can significantly improve the effectiveness of the graph. We're going to go back to code and change it back to where it uses memory. So I'm going to get rid of this line, uncomment this, and also go ahead and uncomment this line, save our file, quit, and now we can move to the next step.
Now it's time to create our first tool calling agent. Let's take a look at the architecture as explained earlier in the LangChain documentation. We can use the method create react agent, and if we just click on that real quick, it will give us a really nice diagram. Create react agent will create an agent which we will then pass as a node to the graph. As you can see, it starts with the start node. It goes to the agent calls a tool, the tool responds back to the agent, and then the agent may choose go back to the end state. And here is a very nice sequence diagram between the user interaction, the agent, and the tools. For our first agent, we're going to create a simple LLM agent. I want to explain this in a greater detail. Normally, you wouldn't add an LLM as a plain agent to a graph. For tool calling, you wouldn't have the LLM call any other tools. I choose to do this because there could be situations where an LLM itself might be enough to answer a user's question. And in that case, the supervisor is unable to handle the question, but an LLM node would be a suitable agent to answer such questions. For example, in our financial agents team, you'd have agents that write files, create Python code and execute code, maybe get GDP data, or Alpha Vantage will get real market data. But none of these tools is specialized in just providing general answers. So that's why we're creating this LLM tool. Okay, back to our browser. So this is the method that we're going to use. Create React agent, and then the resulting agent will pass as a node to our graph. We're going to start at the top by adding two import statements. First, we're going to import the tool, which we'll use as a directive later on for creating the tools. And the second is we're going to import the create React agent. Next, let's define our tools. Here, we're going to use the name LLM tool with the query that is the query to search for. This is a basic LLM tool that will be used to return the user data. And here we also need to import the annotated class. We have added annotated, and we have the tool defined. Next, we need to add our LLM node into our member names. Now, also, let's update our system prompt. So we're going to take the system prompt and replace it with something better encompassing the new LLM node that we just created. Yes, so this system prompt is a lot more appropriate for our purposes. Back in our nodes, let's add our LLM node now. And to do that, we're going to use the create React agent. And for the tools, we're going to pass the LLM tool that we created earlier. For LLM, we're going to pass our standard LLM. And this method itself will create our LLM agent. Tools parameter is a required parameter, so you can't create an agent without a tool for this React architecture. Now let's add the node. We're going to define our LLM node by passing the agent state, and the result will be the LLM agent.invoke. We're going to use this LLM agent, the result of create React agent, and we're going to pass the state. Here we also need to import the human message. Okay, now human message is also imported. LLM node itself is now defined by taking the LLM agent and calling .invoke with the state. The return will be the state with the last message and with the name LLM node. That's our node definition. Now we need to add the node into our graph. Here we are adding LLM and the node definition here with the keyword LLM, because that's how we defined it in the members. So now effectively this node is part of the graph. We can now rerun our graph and we should see the supervisor communicating with the LLM agent. Let's go ahead and do that. We're going to save this file, open back the terminal, and run our graph. We can launch our graph with a simple hi and see what results we're getting this time. And now, differently from previous run, the supervisor was able to route it to the LLM node, and we received the message back, "Hello, how can I assist you today?" We have a functioning graph now with one agent, that is the LLM agent. Let's check out the graph. The supervisor node goes into the LLM agent, which we used by create agent method. Inside this subgraph, it has its own lifecycle with its own start state, the state modifier. It calls our LLM. It uses the tools, the LLM tool, and then when it's finished, it goes back to the supervisor. If we go back and check our LangSmith, so let's go ahead and do that. Let's take a look at our LangSmith execution. Okay, so this is our LangSmith execution. Let's maximize that. And we'll see that the supervisor received the human message that was hi. And then the LLM agent was called. And this is the subgraph inside the LLM message. And this is the response received from the LLM. Really, really good. The supervisor directed the message to LLM. And by the way, if we check the supervisor's next output, it should be LLM. Yes, so next is LLM. Now we have added our first agent node to our network. So a quick summary. In this first step, we started with a blank supervisor node and we added a LLM agent. In order for the LLM agent to work, we needed to create an LLM tool, which is nothing but just calling the LLM with the invoke method. So you could do the same thing that we're doing with this agent network by a straight LLM invocation. It's literally the same. It's just sending a message to the LLM model, and the LLM model is providing an answer. But it's good practice, in my experience, to include an LLM agent as part of these agentic flows, even in the React architecture, so that you can receive answers to simple queries or simple trivial questions without having to go with more specialized agents that use other tools. Okay, good. Now we can move on to adding our second agent to our network. In this section, we're going to add a file read and write tool. Before we do that, let's head out to the LangChain's website and check out the page about their tools. There is a list of tools that are available for us, and this is a really nicely put together web page with a lot of different tools. You have tools for web browsing, database access. The one that we're interested in is this file system toolkit. What we'll notice here is the file management toolkit gives us ability to read files, delete, file tool, file search tool, move, read, write, list directory. So here's a list of the available tools, and this is what we're going to use for this agent. Now let's jump back into Visual Studio Code and create our file reading agent. We're going to start at the top by adding the import statement. Next, we're going to define our tools. So in our tools section, right after the LLM tool, we're going to define our file tool. And in this case, there are three tools that we're going to use. And the selected tools here are read file, write file, and list directory. Next, we're going to add our file tool into the list of members. So we're going to name it file writer. Next, we're going to enhance our system prompt. Now that we have a new agent, let's define its responsibilities so that the supervisor knows which tasks to redirect to the file writer. Next, we're going to define our node. Our file agent will, again, we're going to use the create React agent, passing the LLM, and as tools, we're just going to pass the write tool. Once the file agent is created, now let's go ahead and create our file agent node. This will invoke the file agent.invoke and passing the state. So it's very similar to what we did with our LLM agent. We're just using the tool that is the write tool. Okay, so that's done. The only thing remaining is to add it to the builder graph. Right after add node LLM, we're going to come here and add our new node, the file writer and the file node. Our graph is now complete. I'm going to go ahead and kill this execution, save our file, and run it one more time. Okay, let's give it a quick test. I will create a simple prompt to ask for a sequence of 10 numbers and their squares and ask our graph to write it to a file in the data folder. And now the supervisor kicked in, and the first agent in the graph is the LLM agent. And the LLM agent calculated the numbers and then forwarded to our file writer agent. And the file writer agent created a file. It's a txt file, and we can see that there are 10 rows with the squares of these numbers. This actually looks quite good, but imagine that I want a CSV file. Because we have memory, I'm going to now prompt to modify this and write it as a CSV file. Now the supervisor kicked in, and you will notice that it went straight to the file writer because the numbers are already calculated. It doesn't need to go to the LLM agent or to any other agent in the graph. So this is super cool. Having memory saves so much time. Here is the CSV with all of our numbers. Let's take a quick look at our LangSmith. So this is my last command, but before that, there was a created sequence of 10 numbers. So the LLM node created the 10 numbers and their squares, even recommended a Python script, but currently we don't have a Python agent. And then the file writer took these 10 numbers and created a file numbers and squares.txt in the data folder. And then I asked it to make the same with the CSV file, and now the file writer created a CSV file. So that's all very good. Going back to the code editor, let's inspect our graph image. Now we have two agents, the supervisor working with the LLM and the file writer, and of course the end node here. Our graph is growing. In this case, we have added a simple LLM node first, and now we've added a file writer node. With this step-by-step approach, we'll keep adding more agents to our graph. This point is important, and the reason I structured this tutorial to be a step-by-step and agent-by-agent is because at the end of the day, every agent should have a purpose. It's step-by-step, and you see the growth of the graph from a very simple basically a seed of an agent graph with only a supervisor. Imagine a boss but no workers, and the boss is incapable of doing any other work. That was our initial. If you look at the start and the supervisor and the end node, was our initial seed of agent network. And then we added a LLM node, and then we added a file writer node, and now we have a bit of an agent graph that can get some data from the LLM and write it to the file system. But beyond that, it's not very capable just yet. So we're going to keep adding more nodes. Okay, now in this section, we're going to add an agent that will execute Python code. We'll use something called Python REPL, which is a tool provided by LangChain. So let's go take a look at the tool itself from LangChain's website. In the tools page here, we're going to look for REPL, Python REPL, and you want to click this to go to its page and read the description. This is super cool. Sometimes for complex calculations, rather than have an LLM generate the answer directly, it can be better to have the LLM generate code to calculate the answer and then run the code to get the answer. In order to easily do that, we provide a simple Python REPL to execute commands in. And here's a caution that REPL can execute arbitrary code. I mean, that's kind of common sense. And there are ways how to make this execution more secure, perhaps by using a Docker container, but we're not going to get into that in today's tutorial. But basically, here's how you can use Python REPL. Here's an example. So we're going to get some of this code and use it in our code editor today. Back in our code editor, let's start with the import statements. For this, we're going to use two imports. One will be the Python REPL that we just saw, and the other one will be matplotlib. And we're going to need matplotlib and instruct our REPL agent, because when creating charts with matplotlib, sometimes they fail. And so we'd like to make our agent a little bit hardened and fail safe when using matplotlib. So we're going to pass a couple of directives inside the agent coded. With the imports done, now let's go ahead and define our tool. Right under the file management tools, we're going to come and use the same REPL statement from the example on LangChain's website. Now our tool definition will be a little lengthy, but I will explain every line what we're going to be doing. We're defining it with the directive tool, and we're going to call it a Python REPL tool. The explanation here is the Python code to execute using instructions such as generating CSV or chart files. Here, we're also explaining inside this Pydantic class the purpose of this coder, and the more explicit this is, the better the generated code and executed Python code is. In fact, I even go so far as to provide examples and where to plot and where to write the files when they're needed. Because sometimes the LLM will ask the coder agent to write the plot file directly instead of the file writer agent, and sometimes it will ask the file writer agent. So in cases where you need this to execute as a standalone agent, it's good to have a descriptive and highly prescriptive system prompt for this agent so it doesn't swear off of its intended purpose. Here in the try and catch block, we're also including the matplotlib use ag, and this is a special statement that avoids some of the matplotlib issues later on. What we're doing is we're doing REPL run the code, and the code will be the one that will be generated by the LLM. So the LLM will pass the code to this agent, and the agent will just execute the code. So we've created our tool. Now let's go to our members array and add the coder name here. We're just simply going to call it coder. We're also going to improve our system prompt for the supervisor. So let's just add some statements for our coder agent now for calculations, visualizations, charts, CSV files to use the coder worker. Now we go to our nodes, and we're going to add a node for coder right after the LLM node. We're going to use the create agent with LLM and passing the Python REPL tool. Once our agent is created, now it's time for us to create a code node. And for this, we're going to use the very same structure we used for our other nodes. We're just going to pass the agent state. We're going to invoke the graph and get the last message and return that with the name coder. We should add the coder back to our builder node. So we're just going to do builder add node coder code node so that it's now part of the graph. We have added our Python REPL code execution agent. Now let's give it a shot. We're going to ask a very simple question to calculate the average of the first 10 numbers and create a bar chart. What I expect to see is a bar chart of the first 10 digits with a horizontal line representing the average. And in this case, our supervisor directed our flow straight into the coder agent, and the coder agent executed and created this new image called barchart.png. So let's take a look at this barchart.png, and we see 1, 2, 3, 4, 5 up to 10. This is 10 numbers, and the average value is here. Of course, this is a very rudimentary chart, but it shows that our agent is working and that our flow is executing. And by the way, the supervisor agent here made a smart choice. It didn't go to the LLM or the file writer node. It went straight to the coder node. So let's take a look at our graph now and see how it looks. Yes, so we have the LLM node, we have the file writer node, and we have the coder node. It's a network with 3 agents and a supervisor. Now let's take a look at our Langsmith calculate the average of first 10 numbers. The supervisor's output here is directly to Coder. Coder now uses tools. So it uses the Python REPL tool. Now the cool part here is that you can see the Python code that's being passed from the LLM to be executed using NumPy and using matplotlib. And here is the calculation, and here is the averages, some prompting, and with some more guardrails, this chart obviously can be customized. And finally, it goes back to the supervisor, and now it's the end. All in all, good execution. Now let's go back to our code editor. And here, let us try something a little bit more complicated. The question is, find the most recent inflation rates of Germany, Switzerland, and Austria, and save them in a CSV file and create a bar chart with the average displayed as a horizontal line. And now the LLM provided some data. However, this data was inconclusive, and as a result, the graph ended with nothing produced. This is a good example of how LLMs struggle because they lack current data. And this is also a good opportunity to add a new node. In this node, we're going to create an agent to perform research. And for that, we're going to use Tavily search, one of the tools available. So let's go ahead and do that. There are a number of tools available, and let's start this section by going to LangChain's tools page and just taking a look at the available search tools. Okay, on this page, you will see that under the search section, there's a number of search vendors and toolkits available. There's Bing, Brave, Exa, Google Search. Gina Search is also very interesting and provides 1 million response tokens free. But what we're going to use today is Tavily Search. And Tavily gives you 1,000 free searches per month, which is amazing for doing quick prototypes or just having a developer account. We're going to click this Tavily search and just look at the details of how to set it up, what libraries we need. And the first thing you're going to see here is that we're going to need to get our API keys from Tavily's website. So head out to tavily.com and sign up for a free developer account. I've already done that. And once you're in, you will see your API keys listed here. You'll want to copy that key. And now when you come back to Visual Studio Code, you will want to insert that into your .env file. So I have a location here for my Tavily API key, and this file will be included in the GitHub repo. So just clone this file into .env and paste your Tavily API key so that the script can recognize it automatically. So once you have your Tavily key, let's go ahead and add our search agent to our network. We're going to start at the top and add our imports for the Tavily search tool. For this, we're going to import from LangChain Community Tools Tavily Search, and the class name is Tavily Search Results. Next, let's define our tool. In the Tools section, we're going to come down here and define the Tavily tool as Tavily Search Results, where the maximum results is 5. Next, let's go ahead and update our members array by adding the researcher as a node to our members. Next, we're going to add a new item to the system prompt so that our LLM knows when to redirect control of the graph to the researcher nodes. So basically what we added was start with the LLM and then call the research tool only when the LLM tool results are inadequate. This applies to situations where, let's say, we're asking for current GDP data or current inflation data or unemployment data that is simply not part of the LLM. Inflation data and unemployment data usually gets released once per month. And for that to be current, a search tool like Tavily would bring those most current results rather than relying on LLM data. Okay, so we've updated our system prompt. Now we're going to add our node and our agent. So for this, I'm going to go ahead and just create a research agent with the create react agent and passing the Tavily tool as the tool. And the state modifier, basically our system prompt here is that you're a researcher, do not do math, answer to the user's question, you have access to the following tool, Tavily Search, use them wisely. We're going to create a research node that will just invoke this agent. And finally, we're going to add the research node to our builder. That is pretty much all we need to add the Tavily Search. Let's give it a try. The question is, find the most recent inflation rates of Germany, Switzerland, and Austria, save them in a CSV file, and create a bar chart with the average displayed as a horizontal line. In the previous iteration, our graph struggled with this question. Let's see if it's going to do better this time. Immediately, it routed it to the researcher, so now Tavily is performing an internet search. And now the internet search came with the results, and it's being routed to Coder. And now the Coder finished its job and it saved the file under data. And sure enough, the most recent data is from 2023. And we have Germany, Switzerland, and Austria. We're going to give it a couple more prompts, but before we do that, let's take a look at our graph and see how it looks now. So we have the supervisor, we have the researcher added, the coder, the file writer, and the LLM. And now it's also a good time to go and take a look at our LangSmith. We can see here that supervisor was the first called agent, and after that researcher, and researcher used the Tavily search results. And here's the JSON that came from the search results. This is super cool that it can be inspected. And we also see the sources for this. So what was used here was tradingeconomics.com, Germany inflation CPI. They have gathered sources. So we set 5 maximum. There is another search result. And finally, Coder agent took over with all the data that was provided by the researcher. Here are the precise inflation rates, by the way, 3.8, 2.1, and 7.8. And now the Coder was able to create our chart. The supervisor then ended the execution. Okay, let's go back to our code editor. And now let's try another question. So first node to execute is researcher. There is an internet search being performed on San Francisco and Zurich. And we start seeing some numbers that are flowing. The name of the chart will be cost salary comparison. So let's take a look at cost salary comparison PNG. So that's the first chart. And San Francisco, the blue bar is cost of living, and the orange bar is average salary. And I assume these are USD per month. And Zurich seems compatible in terms of cost of living, but average salaries are about 10% lower according to this. In the next section, we're going to add another tool to the mix, which will be a specialty tool called Vantage, which we'll then use to bring real-time market data into our graph. Specifically, we'll look into the natural gas prices. It is now time to bring real-time market data into our graph. We're going to use Vantage, a tool that is also available on LangChain's website. So let's go ahead and take a look at the tool itself first. We're going to go to our browser. In our tools section, we're going to look for Vantage. It provides real-time historical financial information. You can scroll down and see some of the available tools and some of the available APIs. One thing that we're going to need is the Vantage API key. To get this, head out to the alphavantage.co. You can check the stock market API and you can get stock market data, news, sentiments, and these are specifically built for data analysis, generative AI applications, for LLM, AI agents, what we're using it, RAG. You can just hit this get free API key. And once you do that, you can just fill in this form and get your free key. Now back in Visual Studio Code, just populate it inside .env. So once we start using the tool, the key is available automatically. Let's start by adding our imports first. For this, the only import we need is the requests. That's what we're going to use for the Vantage tool. Next, let's define our tools. Scroll down to the end of the tools section right after Tavily. And first, we're going to define a function that we will use to get the natural gas prices. We're going to make a get call to this API endpoint with the following parameters. Function will be a natural gas, and this is all well documented on Vantage's website. To get natural gas prices, you pass the function name as natural gas, the API key we get from our environment variable, and then we just parse the response JSON and return the data. That's our simple function to get natural gas. Now let's build a tool that will use this function. We're going to use the tool directive, and we're going to call this the Alpha Vantage tool. The result will be the get natural gas function that we just defined. If there's any exception, we'll just return the exception. That's pretty much it with the tool. Now let's go ahead and add this to the members. And now let's update our system prompt so that our supervisor knows how to use the Alpha Vantage tool. At the end of the system prompt, we're just going to add that if you're asked to get historical data for natural gas prices, do not use the research tool, go straight to the Alpha Vantage tool. And the reason for that is that sometimes the LLM gets confused which tools they need to use, and it's good practice to just be very prescriptive and say for natural gas prices, or for the latest Forex exchange prices, or for the latest real-time market data, use the Alpha Vantage tool. That's what we're doing here with the system prompt. And one thing you may notice is that our system prompt is growing in size and detail. And that's a good thing at the end, because the more guardrails you put around the system prompt and the supervisor, the better you would utilize the entire network. Finally, let's define our nodes and add them to the builder. I'm going to come to the end here and define the Alpha Vantage agent with the create react agent first, passing the Alpha Vantage tool, and then we're just going to create a node and we're going to pass the name Alpha Vantage. Now let's add it to the builder, and with that change, now the Alpha Vantage tool has been added to our agent graph. So let's give it a shot. Plot a chart of the natural gas historical data for the past 5 years. We see that our supervisor correctly routed the request to the Alpha Vantage tool. Alpha Vantage is making a call to its API with the function for natural gas prices. We received the data from the natural gas prices API, and that got routed to the coder. And now the coder is processing this data and it's creating Python code which will get executed with REPL. And now the chart has been created at naturalgasprices.png. So let's take a look at this chart that's being generated. Henry Hub natural gas spot price for the last 5 years. We see from 2017 to 2025. And this is an example of how cool custom tools like Alpha Vantage are, because we have data up to the minute almost. We're nearing the end of 2024 and we have the natural gas prices. As we can see, they spiked somewhere around October of 2022, and there's been a steep decline since. Let's take a look at our graph and see how it's growing. Sure enough, now we have the Alpha Vantage, the researcher, the coder, the file writer, and the LLM 5 tools that are being managed by the supervisor. Now let's go ahead and create another query that is related to natural gas. Our question this time is plot a bar chart of the natural gas prices for the past 5 years and overlay with Germany's GDP for the same period. Now we're asking for 2 data points, the gas prices. We already have them from the previous question, so that shouldn't be a problem. But now the supervisor also forwarded it to the researcher node. So the researcher is trying its best to get the last 5-year GDP data for Germany. So let's just take a look at this. We can see that the chart is somewhat related and relatable, but it's not a great looking chart. So the red line is the GDP in trillions, and from 2017 to 2024, the Germany GDP seems to have grown from 2 trillion to 4 trillion, which honestly is hard to believe. And this is one of the pitfalls of internet research, because it's not easy to understand where this data came from unless we go and take a look at, we know the natural gas prices seem accurate because they're coming from Alpha Vantage, but these GDP numbers seem a little skewed. So we've seen some of the successes of the Alpha Vantage tool, but also some of the shortcomings, especially when it comes to getting some specific data such as the GDP. Our Tavily search tool, as good as it is, it's not able to get structured GDP data from internet sources. And for that, let's go ahead and create our last tool, which will be a custom tool that will pull GDP related data from IMF site. Okay. Now it's time to add our final tool, which will pull GDP data from IMF's website. Let's go ahead and open our browser first and navigate to IMF's API. You can get this from imf.org. I will provide the links in the description of the video so you can go and browse these APIs. The one that we're looking for is, this is providing time series. So feel free to just click on indicators, for example, or countries, list of countries. These are the country codes. So for example, for Germany, you would look for DEU. What we'd like to do is retrieve all values for real GDP growth. So this will be in percentage points, and it will be for a country. In this case, it goes back to 1980. So we're getting close to 44 years of GDP growth data, both positive and negative numbers here. Quite an extensive API endpoint, public, no key that's required to pull in from this API. So we're just going to create a custom tool and create an agent that will, when asked for GDP data, will come and use data from this API. So with that said, let's go and open our code editor. We're going to go to the bottom of our tool definitions here. For this, we're going to create a simple function, get GDP data, where we're going to pass a country code as a string, and we're going to use requests to get JSON data from this API endpoint, parse the JSON, and then return the data in this string. We'll let the LLM pass the country code to our tool. The tool itself will be a GDP tool. It will receive the country code as a string and then pass it to the method. So our tool definition is ready. Let us add our new agent to our list of members, and we're going to call this GDP researcher. We're going to finalize our system prompt. Let's define our nodes and then add them to the graph. We're going to navigate to the end of our node definitions here and create our GDP agent using the same create React agent, passing the GDP tool. And then we're going to create our GDP node and passing the name GDP researcher, the same name that we passed to our members array. Finally, let's add it to the graph. Builder add node GDP researcher GDP node adds it to the graph. And now it's time to execute our final graph. Before we do anything else, let's inspect our final chart. We see now that we have the LLM, we have the file writer, we have coder, we have researcher, alpha Vantage, and finally our GDP researcher tool. Compare the GDPs of US and China for the past 10 years and plot a bar chart. Immediately got routed to GDP researcher, and now coder is executing based on the data supplied by GDP researcher. And now we can see that an image called GDP comparison has been created. So let's take a look at this. We can see here that the data coming from the GDP researcher is solid, and it's much better compared to the GDP data coming from just a straight up internet search. Red represents China, blue represents the US. And as we can see in 2013, the Chinese GDP rate was close to 8%, while the US was at 2%. Let's try another query. Find the most recent GDPs of Germany, Switzerland, and Austria and create a bar chart. Initial node GDP researcher. Now it's going to coder. The data is here already. The chart that's being generated is GDP comparison chart 2023. And the most recent year here is 2023. That's what it was able to find. And as we can see, for 2023, Germany shrank by about 0.2%, while Austria shrank by close to a full percentage point, while Switzerland grew by 0.6%. So this data is a lot more realistic compared to the initial chart that we were receiving GDP numbers for the last 2-3 years. Let's ask one more question. Create a correlation chart of the natural gas prices compared to GDP rates for the US in the past 10 years, starting with Alpha Vantage. We'll get the last 10 years natural gas prices first, and now going to coder and gas GDP correlation PNG. And let's take a look at this. So this is the correlation between natural gas prices and GDP growth rates in the US between 2013 and 2022. So this is the price of natural gas in dollars per million BTUs, and this is the GDP growth rate. So this is a correlation chart of those two variables. Okay, so with that, we have concluded our tutorial. Let's just take a quick look at the final result. We started with the start node. Our supervisor is then forwarding to the related agent in a React architecture. We added an LLM node just in case if no other tool is needed. Then we added a file writer, a coder, a researcher, Alpha Vantage for real-time market data, and the GDP researcher to bring GDP data per country from the IMF public APIs. Okay, that's a wrap. I hope you enjoyed this tutorial and you learned something new. If you like this type of content, make sure to subscribe to this channel for future updates and join our Discord server for deeper conversations. Thank you for watching.